Welcome, and thanks for being here. You can get comfortable. There's nothing you need to do right now. No need to focus too much. Just let the words be in the background. Some thoughts might catch your attention, others might drift away, and that's perfectly fine. If you enjoy this kind of calm space, you can leave a like to support the channel and subscribe if you'd like to come back again. It really helps, and it keeps this space going. For now, just take it easy. Let the sound settle, let the day fade a little, and allow yourself to rest. When we ask whether reality existed before observation, we are not asking a mystical or poetic question, but a carefully defined scientific and philosophical question about what physical systems are like in the absence of measurement. And to approach this question calmly, we must first clarify what we mean by the word reality, because in everyday language, reality often means everything that exists, while in physics, reality usually refers to the physical state of systems described by measurable properties such as position, momentum, energy, and structure. And this distinction matters because physics does not attempt to describe existence in an abstract sense, but instead attempts to describe how systems behave and how their properties can be predicted. And similarly, the word observation does not necessarily mean a conscious human looking at something, but rather any physical interaction that extracts information from a system, and this includes interactions between particles, interactions with measuring devices, and interactions with the environment. And by starting with these grounded definitions, we avoid unnecessary confusion and keep the discussion anchored in physical theory. And in classical physics, which describes everyday objects and large-scale systems, reality is assumed to be objective and well-defined at all times, meaning that objects possess definite properties whether or not anyone is observing them. And a rock has a location, a temperature, and a shape, regardless of whether it is being measured. And this view fits well with common intuition and with centuries of experimental success. And for most practical purposes, classical physics remains an excellent approximation of how the world behaves. And within this framework, the idea that reality might depend on observation does not arise, because properties are simply there, waiting to be discovered. However, when physicists began studying nature at very small scales, such as atoms and subatomic particles, they encountered behavior that could not be explained using classical assumptions. And this led to the development of quantum mechanics, which describes physical systems in terms of probabilities rather than definite values. And in quantum theory, systems are represented by mathematical objects that encode a range of possible outcomes rather than a single determined state. And this shift introduces a new kind of question, because if a system is described as a set of possibilities, what does it mean for the system to be real before a measurement selects a specific outcome? And it is this question that gives rise to the modern form of the problem. And it is important to note that quantum mechanics does not claim that nothing exists before observation, but rather that the theory itself does not assign definite values to certain properties until a measurement occurs. And this distinction is subtle but crucial, because it means the uncertainty lies in the description, not necessarily in existence itself. And part of the difficulty comes from translating mathematical formalism into everyday language, which can easily create misleading impressions. And throughout this series, we will move slowly through these ideas, examining what quantum theory actually says, what it does not say, and how different interpretations attempt to explain the relationship between observation and reality. And at this early stage,
The most important point is that the question of whether reality existed before observation is not about whether the universe existed before humans, but about whether physical properties are well defined independently of interactions. And keeping this distinction in mind will help us explore the topic with clarity and patience.
To understand how observation enters physics, it is helpful to look more closely at what physicists mean by measurement, because in everyday language, measurement often implies a deliberate action performed by a person using an instrument, while in physics, measurement refers more broadly to any physical process in which information about a system becomes correlated with something else, and this correlation can occur without human involvement. And in classical physics, measurement is assumed to reveal a property that already existed, meaning that the act of measurement does not fundamentally alter what is being measured. And this assumption works extremely well for macroscopic objects, such as measuring the length of a table or the speed of a moving car. And within this framework, observation is passive and reality is independent. However, quantum mechanics introduces a different relationship between systems and measurements, and according to the mathematical structure of the theory, certain properties cannot be assigned definite values prior to measurement, and instead are described by probability distributions. And when a measurement occurs, one outcome is realized from among the possible outcomes, and this realization is often described as the system taking on a specific value. And this does not necessarily mean that the system had no properties before, but it does mean that the theory does not specify which value would appear, only the likelihood of each. And this distinction leads to the impression that observation somehow creates reality. But a more careful interpretation is that observation reveals one particular aspect of a system's potential behavior. And it is also important to recognize that measurement in quantum mechanics always involves interaction, because to measure something, a system must interact with a measuring device, and this interaction changes both the system and the device, and therefore measurement is not a neutral act, but a physical process governed by the same laws as everything else. And this perspective helps remove some of the mystery, because it frames observation as a natural interaction rather than a special metaphysical event. And as we continue, we will examine how classical and quantum descriptions differ, and why quantum theory forces us to rethink certain assumptions about how properties exist before they are measured, without jumping to conclusions about whether reality itself depends on observers. Before exploring the quantum description in greater depth, it is useful to briefly revisit the classical view of nature, because this view still forms the foundation of how we understand most everyday phenomena. And in classical physics, the universe is treated as a collection of objects with well-defined properties at all times. And these properties evolve according to deterministic laws, meaning that if the present state of a system is known precisely, its future state can, in principle, be predicted exactly. And within this framework,
uncertainty arises only from practical limitations, such as imperfect instruments or incomplete information, not from the nature of reality itself. And this leads to a picture of the world in which reality exists independently of observation, and measurement simply uncovers what is already there. And this classical worldview aligns closely with human intuition because it matches our daily experience of solid objects, continuous motion, and predictable cause and effect relationships. And it also provided extremely accurate predictions for centuries, from planetary motion to engineering systems. And even today, classical physics remains the correct description for a vast range of scales and conditions. However, as experimental techniques improved and scientists began probing smaller scales, certain phenomena emerged that could not be explained within the classical framework. And these phenomena included discrete energy levels in atoms, interference patterns produced by individual particles, and statistical behavior that persisted even when experiments were carefully controlled. And these observations forced a shift away from purely deterministic descriptions and toward a probabilistic framework. And it is important to emphasize that this shift did not invalidate classical physics, but revealed that classical physics is an approximation that works well in certain regimes and fails in others. And recognizing this layered structure of physical theory helps prevent an overly dramatic interpretation of quantum mechanics, because it shows that different descriptions apply at different scales. And as we move forward, we will examine how the quantum view modifies, rather than completely overturns, the classical assumption that reality exists independently of observation. Quantum mechanics describes physical systems using mathematical objects that encode probabilities rather than fixed outcomes. And this represents a fundamental departure from classical descriptions, where systems are assigned definite properties at all times. And in the quantum framework, a system is represented by a wave function, which contains information about the range of possible results that could be obtained if a measurement were performed. And this wave function does not specify a single position, energy, or momentum, but instead assigns probabilities to different possibilities. And this does not mean that the system is vague or undefined in a casual sense, but rather that its behavior is governed by statistical rules. And when a measurement occurs, one specific outcome is observed, and the wave function is updated to reflect this new information. And this process is often referred to as collapse, though the word itself can be misleading, because it suggests a physical jump, while in practice, it represents a change in the mathematical description used by the observer. And this is where questions about observation and reality become most pronounced, because the theory does not specify exactly what constitutes a measurement or why a particular outcome occurs, only the probabilities of different outcomes. And this leaves room for different interpretations. And some interpretations treat the wave function as a complete description of reality, while others treat it as a tool for calculating probabilities. And this distinction matters because if the wave function is taken as physically real, then the system may not possess definite properties prior to measurement, while if it is taken as a bookkeeping device, then the system may have definite properties that are simply unknown. And as we continue, we will explore these interpretive possibilities carefully, without assuming that any single view is definitively correct. And at this stage, the key point is that quantum mechanics challenges the classical idea that all properties are always well-defined, but it does not force us to conclude that reality itself only exists when observed. In the classical view of physics, determinism plays a central role. And determinism means that the present state of a system fully determines its future state, provided the governing laws are known. And this idea implies a universe that unfolds like a continuous chain of cause and effect, where every event has a precise physical explanation rooted in prior conditions. And for a long time, this picture was considered not only useful, but fundamentally accurate. And even today, it remains an excellent description for planets, machines, fluids, and most large-scale systems. And within this classical framework, the concept of reality existing independently of observation is straightforward, because properties such as position, velocity, and energy are assumed to have definite values whether or not anyone measures them, and observation merely reveals what is already there. And however, when quantum mechanics entered the picture, it became clear that this classical form of determinism does not hold at very small scales. And instead of precise predictions for individual events, quantum theory provides precise predictions for probabilities. And this shift does not mean that nature becomes chaotic or lawless, but rather that the laws themselves take on a statistical form. And this statistical structure forces us to reconsider what we mean by determinism. And one way to think about this change is that quantum mechanics replaces certainty about individual outcomes with certainty about distributions of outcomes. And this is a subtle but important distinction, because it means that while we cannot predict exactly which result will occur in a single experiment, we can predict with great accuracy how often different results will occur over many repetitions. And this predictive power has been confirmed by countless experiments. And so the question becomes not whether quantum mechanics works, but how its probabilistic nature should be interpreted. And in particular, whether probabilities reflect a lack of knowledge about an underlying definite reality, or whether they reflect something fundamentally indeterminate about nature itself. And this question sits at the heart of the debate about whether reality exists in a well-defined way before observation. And some physicists lean toward the idea that hidden details exist beneath the probabilistic surface, even if we cannot access them, while others accept that indeterminacy may be an intrinsic feature of the universe. And at this stage, it is important to move slowly and avoid assuming that probability automatically implies non-existence or vagueness, because probability in physics is a precise mathematical tool, not a statement about confusion or ignorance. And understanding this prepares us to examine specific quantum phenomena that bring these abstract ideas into sharper focus.
At the quantum level, particles are not described as tiny solid objects following clear trajectories, but as entities whose behavior combines aspects of waves and particles. And this dual description is not a metaphor, but a precise feature of how experiments behave. And when electrons, photons, or other quantum particles are sent through certain experimental setups, they produce interference patterns that are characteristic of waves, and yet when they are detected, they appear as localized impacts characteristic of particles.
And this wave-particle duality is one of the earliest clues that classical intuition is insufficient at small scales. And within quantum theory, the wave-like aspect is captured by the wave function, which evolves smoothly over time according to mathematical rules. And this evolution describes how probabilities change, not how definite properties move through space. And when a measurement is performed, a specific outcome is recorded, and the system is described as taking on a particular value. And this combination of smooth evolution and discrete outcomes creates a tension that has no direct analog in classical physics. And it is within this tension that questions about the role of observation arise. And one way to approach this calmly is to recognize that quantum mechanics does not say that particles are literally waves of substance, nor that they are literally classical particles, but that their behavior is governed by a mathematical structure that has both wave-like and particle-like aspects. And this structure has proven extraordinarily successful at predicting experimental results. And therefore, the challenge lies not in whether the theory works, but in how we should understand what the theory is telling us about the nature of physical systems. And as we continue, we will examine specific experiments that illustrate this wave-particle behavior in a clear and concrete way, and see how these experiments sharpen the question of whether physical properties are defined before they are measured.
One of the simplest ways to explore quantum behavior is to look at situations where a single particle is sent toward multiple possible paths, and the results reveal patterns that cannot be explained using classical ideas alone. And in such experiments, particles are not treated as dividing into pieces, but as existing in a state where multiple possibilities coexist. And this coexistence is described mathematically as superposition, meaning that a system is represented as a combination of several possible states at the same time. And this does not mean that the particle is partly in one place and partly in another, in a physical sense, but rather that the theory assigns non-zero probability to multiple outcomes simultaneously. And as long as no measurement is made, the system evolves according to these combined possibilities. And when a measurement occurs, one definite result is observed, and the other possibilities no longer appear in the description of the system. And this transition from multiple possibilities to a single observed outcome is one of the central features of quantum mechanics. And it naturally leads to the question of whether the system possessed a definite state before the measurement, or whether the definite state only came into existence at the moment of measurement. And it is important to approach this question carefully, because the theory itself does not directly answer it, and instead provides rules for calculating probabilities. And different interpretations propose different underlying pictures. And some suggest that all possibilities are equally real but become separated from each other, while others suggest that a hidden underlying reality determines the outcome even though we cannot observe it. And still others treat the wave function as a tool for organizing information rather than a literal physical object. And what all interpretations agree on is that the mathematical formalism accurately predicts experimental results. And this agreement is more important than any particular philosophical story attached to it. And at this stage,
The key point is that quantum mechanics replaces the classical idea of a single definite trajectory with a description based on overlapping possibilities. And this replacement is what makes the question of pre-observation reality both meaningful and difficult, because it forces us to confront the difference between what is mathematically described and what is physically experienced. When multiple possibilities are present in a quantum system, the question naturally arises of how and when one possibility becomes the outcome we actually observe, and this question is often referred to as the measurement problem. And it does not arise because experiments are poorly performed, but because the mathematical rules of quantum mechanics treat two processes differently. And one process is the smooth, continuous evolution of the wave function over time, while the other is the sudden updating of the description when a measurement is recorded. And the theory itself does not specify exactly what physical event separates these two regimes, and this gap leaves room for interpretation. And one way to think about measurement is to view it as a physical interaction in which a quantum system becomes strongly correlated with a much larger system, such as a measuring device or the surrounding environment. And as this interaction occurs, information about the quantum system spreads into many degrees of freedom, and the system becomes entangled with its environment. And once this entanglement becomes sufficiently complex, interference between different possibilities becomes effectively impossible, and the system behaves as though only one outcome exists. And this process is known as decoherence. And decoherence does not require a conscious observer, but only interaction with the environment. And this perspective shifts the focus away from human awareness and toward physical processes. And it suggests that what we call observation is simply a special case of interaction. And this does not fully solve the measurement problem, because it explains why interference disappears, but not why a particular outcome is experienced. And yet it does show that many aspects of apparent collapse can be understood as natural consequences of physical interaction. And this understanding weakens the idea that reality waits for a mind to look at it, and instead supports a view in which physical processes unfold continuously, with observation being one part of that unfolding rather than its creator. When we combine the ideas of superposition and decoherence, a quieter picture of quantum behavior begins to emerge. And in this picture, physical systems are always interacting, even when no deliberate measurement is taking place. And these interactions constantly entangle systems with their surroundings. And this entanglement gradually suppresses interference between different possibilities, making the world appear classical at large scales. And this explains why everyday objects do not display obvious quantum superpositions, even though their microscopic components obey quantum laws. And from this perspective, definite outcomes do not require a conscious observer, but arise naturally from the complexity of physical interactions. And this shifts the original question slightly, because instead of asking whether reality exists before observation, we begin to ask how definite-looking reality emerges from underlying quantum descriptions. And this is a different kind of question, focused on process rather than existence. And it suggests that reality does not switch on at the moment of observation, but gradually takes on stable form through ongoing interaction. And within this framework, the wave function is not necessarily a catalog of what exists, but a tool for predicting how systems will behave when they interact. And this interpretation allows us to maintain the idea that the universe existed long before observers appeared, while still accepting the probabilistic structure of quantum theory. And at the same time, it acknowledges that certain properties may not have definite values until interactions make them stable. And this balanced view avoids the extremes of saying that nothing exists without observation, and also avoids the assumption that all properties are always sharply defined. And as we continue, we will look at specific experiments that illustrate these principles in concrete ways and see how they deepen our understanding of the relationship between possibility, interaction, and outcome. One of the most well-known experiments that illustrates the strange features of quantum behavior is the Double-Slit Experiment, and its importance comes not from complexity, but from clarity, because it reveals how a single particle can display both wave-like and particle-like behavior, depending on how the experiment is arranged. And in a simple version of the experiment, individual particles, such as electrons or photons, are sent one at a time toward a barrier containing two narrow openings, and beyond the barrier is a screen that records where each particle arrives. And when no attempt is made to determine which opening the particle passes through, the pattern that gradually builds up on the screen shows a series of bright and dark bands, known as an interference pattern. And this pattern is characteristic of waves spreading out and overlapping. And yet the particles arrive as localized points, one by one. And this means that each particle behaves in a way that contributes to a wave-like pattern, even though it is detected as a particle. And when detectors are placed at the openings to determine which path each particle takes, the interference pattern disappears, and the results instead match what would be expected if particles traveled through one opening or the other. And this change occurs even if the detectors are extremely gentle. And this shows that the mere availability of path information alters the outcome. And this experiment does not imply that human awareness creates reality, but it does demonstrate that the experimental arrangement, and therefore the physical interactions involved, determine which properties become well-defined. And this supports the idea that properties are not simply waiting in a fixed state to be revealed, but emerge through interaction. And as we move forward, we will examine what this implies for the idea of an objective reality that exists independently of observers. To move forward carefully, it helps to look more closely at what the wave function actually represents, because much of the confusion about observation and reality arises from how this mathematical object is interpreted. And in quantum mechanics, the wave function is a compact way of encoding all the information needed to calculate probabilities for different measurement outcomes. And it evolves over time according to precise equations. And this evolution is continuous and deterministic, meaning that if the wave function at one moment is known, its future form can be calculated exactly. And this deterministic evolution exists alongside the probabilistic nature of measurement outcomes. And this coexistence of deterministic evolution and probabilistic results is one of the defining features of quantum theory. And it is important to recognize that the wave function itself is not something that can be directly observed. And what we observe are always outcomes of interactions, such as detector clicks or recorded positions. And this separation between mathematical description and observed result leaves room for multiple interpretations. And some physicists interpret the wave function as a real physical entity, meaning that the superposition of possibilities literally exists in the world, while others interpret the wave function as a tool for organizing knowledge about a system, rather than a direct description of what exists. And in this second view, the wave function represents information about potential outcomes, not a physical mixture of states. And this difference in interpretation has significant consequences for how we think about pre-observation reality. Because if the wave function is physically real, then reality itself may be spread across multiple possibilities before measurement. While if the wave function is informational, then reality may be definite even though we do not know its details. And quantum mechanics itself does not choose between these interpretations, because both lead to the same experimental predictions. And this neutrality is a source of both strength and discomfort. And it shows that physics can be extraordinarily successful at predicting outcomes without providing a single agreed-upon picture of what is happening underneath. And this situation encourages a cautious attitude where we distinguish between what the theory calculates reliably and what we infer philosophically. And at this stage, the most stable conclusion is that quantum mechanics does not state that reality is created by observation, but rather that the theory's description of certain properties becomes definite only when interactions occur. And this leaves open the possibility that reality exists continuously, even if some aspects of it cannot be sharply defined until measured. And holding this balanced position allows us to continue exploring the topic without forcing premature conclusions.
Information plays a central role in modern physics, and this role becomes especially important when we talk about measurement, because measurement is not simply about seeing something, but about establishing a correlation between a system and another physical system, such as a detector, a memory device, or the surrounding environment. And when such a correlation forms, information about the state of the original system becomes encoded elsewhere. And this encoding allows predictions and comparisons to be made. And in quantum mechanics, information is treated as a physical quantity, meaning that it is carried by physical systems and constrained by physical laws. And this perspective helps clarify why observation does not need to involve awareness, because information can be recorded and transmitted without any conscious participation. And from this viewpoint, the question of whether reality existed before observation becomes closely tied to the question of whether physical systems have states independent of information transfer. And one way to approach this is to recognize that interactions occur constantly throughout the universe, long before any measuring devices or observers existed. And particles collide, fields interact, and energy is exchanged, and all of these processes involve correlations and information flow. And this suggests that the universe has always contained ongoing processes that resemble what we call measurement, even if no one was there to label them as such. And this perspective weakens the idea that observation brings reality into existence, and instead supports a view in which reality is shaped and refined through continuous physical interaction. And at the same time, quantum mechanics reminds us that not all properties become well-defined through every interaction. Only certain types of interactions lead to stable records that behave classically.
And understanding which interactions produce stable information is an active area of research, and it lies at the heart of how classical reality emerges from quantum processes. And this gradual emergence provides a more nuanced answer to the original question, suggesting that reality did not suddenly appear when observed, but gradually acquired definite features as interactions accumulated.
A natural idea that arises when people encounter quantum probabilities is the possibility that hidden details exist beneath the surface. Details that determine outcomes even though we cannot observe them. And these hypothetical details are often referred to as hidden variables. And in this context, a hidden variable theory would propose that particles always possess definite properties, but that quantum mechanics does not fully describe those properties, and instead provides only statistical predictions because some information is missing. And this approach preserves a classical-style picture of reality existing independently of observation, while accepting that our current theory is incomplete. And several physicists explored this possibility in the early development of quantum mechanics, and some specific hidden variable models were constructed. And however, theoretical results and experimental tests placed strong constraints on what kinds of hidden variable theories are possible. And in particular, a class of results known as Bell's inequalities showed that no theory based on local hidden variables can reproduce all the predictions of quantum mechanics. And experiments have repeatedly confirmed violations of these inequalities, supporting the quantum predictions. And this does not mean that all hidden variable theories are impossible, but it does mean that any such theory must involve non-local effects, meaning influences that do not respect ordinary notions of spatial separation. And this requirement is difficult to reconcile with classical intuitions, and it complicates the idea of a simple underlying reality with definite properties at all times. And yet, some physicists still explore non-local hidden variable models, such as pilot wave theory, which propose a definite underlying reality guided by a wave function. And these models reproduce quantum predictions while maintaining determinism. And the existence of such alternatives shows that quantum mechanics does not force a single philosophical conclusion, and that the question of pre-observation reality remains open. And this openness reflects the fact that physics can tell us how systems behave, but often leaves multiple consistent ways of interpreting what that behavior means. Another important question related to observation and reality concerns randomness. And in everyday language, randomness often implies disorder or lack of cause. But in physics, randomness refers more specifically to outcomes that cannot be predicted with certainty, even when the governing laws are known. And quantum mechanics predicts certain events only probabilistically, and no additional information within the theory allows us to determine which specific outcome will occur in an individual trial. And this has led many physicists to conclude that randomness is a fundamental feature of nature, rather than a reflection of ignorance. And if this view is correct, then the universe is not fully deterministic at its deepest level. And this has implications for how we think about reality before observation, because it suggests that certain future properties do not exist as definite facts until interactions occur. And however, it is important to separate unpredictability from non-existence, because a process can be unpredictable without being unreal. And for example, radioactive decay is unpredictable in its timing, but the unstable nucleus itself exists prior to decay.
And similarly, quantum randomness may describe limits on prediction rather than absence of physical states. And some interpretations treat quantum probabilities as reflecting genuine indeterminacy, while others treat them as emerging from deeper processes that we do not yet understand. And once again, quantum mechanics itself does not settle this question, and instead provides a mathematical framework that works regardless of which interpretation one prefers. And this neutrality suggests that the question of whether reality existed before observation cannot be answered solely by pointing to randomness, and instead requires careful consideration of what the theory actually claims and what it leaves open. And maintaining this careful distinction helps avoid overstating what quantum mechanics implies about the nature of existence.
The double-slit experiment can be extended in ways that make the role of information even more explicit, and these extended versions help clarify what changes when we attempt to learn which path a particle takes. And in so-called which-path experiments, detectors are placed in such a way that they can, in principle, record through which opening a particle passes. And when this information becomes available, even if no one actually looks at the data, the interference pattern disappears. And this shows that it is not human awareness that matters, but the physical possibility of distinguishing paths. And when the experimental setup is arranged so that which path information is erased or made fundamentally inaccessible, interference can be restored. And this phenomenon is known as quantum erasure, and it demonstrates that what matters is not observation in a psychological sense, but the structure of physical correlations. And these results reinforce the idea that measurement is best understood as interaction, and that physical systems respond to how they are coupled to other systems. And from this perspective, reality is not created by observation, but shaped by networks of interaction. And this view also explains why the universe could exhibit well-defined behavior long before any observers existed, because interactions between particles and fields were already occurring, and these interactions established correlations and outcomes. And the existence of quantum erasure experiments does not imply that the past is changed retroactively, but rather that the description of correlations depends on the complete experimental context. And this subtlety can be difficult to translate into everyday language, but it highlights an important theme, that quantum mechanics is a theory about relationships between systems, rather than a theory about isolated objects with standalone properties. And understanding this relational character brings us closer to a coherent picture of how reality can exist independently of observation, while still exhibiting context-dependent behavior. Another way of approaching the question of pre-observation reality is to consider how quantum behavior scales up to larger systems. Because if reality depended on observation in a strong sense, it would be difficult to explain why macroscopic objects appear stable and well-defined. And yet, in everyday experience, tables remain solid, mountains remain in place, and planets follow predictable orbits regardless of whether anyone is watching. And this stability arises because large systems are composed of enormous numbers of particles that are constantly interacting with each other and with their environment. And these interactions produce rapid decoherence, which suppresses quantum interference between different possibilities. And as a result, macroscopic systems behave in ways that closely approximate classical physics. And this emergence of classical behavior from quantum rules does not require conscious observers, but only complex interaction.
and this provides a natural explanation for why the world appears definite at large scales, even though it is described probabilistically at small scales. And from this perspective, reality does not switch on when observed, but gradually takes on stable form as systems become entangled with their surroundings. And this gradual emergence supports a layered view of reality, where quantum descriptions apply at small scales, classical descriptions apply at large scales, and both are part of a consistent overall picture. And this layered view avoids the extreme conclusion that reality itself depends on observation, while also avoiding the claim that all properties are always sharply defined, and instead suggests that definiteness is an emergent feature arising from interaction and complexity. And this way of thinking allows us to say that reality existed long before observers, even though the way reality is described changes depending on scale and context.
Some interpretations of quantum mechanics go further than others and propose that all possible outcomes of quantum events actually occur, each in its own branch of reality. And this family of ideas is commonly referred to as the many worlds interpretation. And in this view, the wave function never collapses, but instead evolves smoothly and continuously at all times, according to the standard equations of quantum mechanics. And when a measurement-like interaction occurs, the combined system of particle, measuring device, and environment becomes entangled. And this entanglement leads to the formation of multiple branches, each corresponding to a different possible outcome. And in each branch, the system appears to have taken on a definite value, and an observer within that branch experiences a single consistent result. And this approach removes the special status of observation as a process that selects one outcome, because no selection is assumed to occur, and instead, all outcomes exist simultaneously in separate, non-communicating branches. And from this perspective, reality before observation consists of a vast superposition of possibilities structured in a highly ordered mathematical way, and observation simply places an observer within one particular branch of that larger structure. And it is important to emphasize that this interpretation does not modify the equations of quantum mechanics, but rather adopts a particular way of understanding what those equations imply about reality. And like other interpretations, it produces exactly the same experimental predictions, and therefore cannot currently be confirmed or ruled out by observation. And the appeal of the many worlds interpretation lies in its internal consistency, because it avoids the need to explain when or how collapse occurs, and instead treats the wave function as a complete and literal description of physical reality. And at the same time, this interpretation raises difficult conceptual questions because it implies an enormous number of parallel branches that cannot interact or be directly detected. And this challenges everyday intuitions about what it means for something to exist. And regardless of whether one finds this picture convincing, it demonstrates an important point, that quantum mechanics does not force us to conclude that reality is created by observation, and instead allows the possibility that reality always exists in a rich, multi-layered form, even when no measurements are performed. And in this sense, the many worlds interpretation offers one coherent way of answering the original question by suggesting that reality existed before observation, but not as a single definite history, and instead as a structured set of many coexisting possibilities.
Another approach to understanding the relationship between reality and observation focuses on the idea that physical properties may be relational rather than absolute, meaning that properties do not exist as standalone attributes, possessed by a system in isolation, but instead exist only through interactions between systems. And in this view, a physical state is defined by how a system is related to other systems, rather than by an independent internal label. And this does not imply that nothing exists on its own, but rather that what exists is a network of relationships that together form physical reality. And for example, a particle may have a well-defined position relative to one measuring device and a different well-defined position relative to another, and both descriptions can be valid within their respective interaction contexts. And this relational perspective fits naturally with the mathematical structure of quantum mechanics, which describes correlations between systems more directly than it describes intrinsic properties of isolated objects. And within this framework, asking whether reality existed before observation becomes a question about whether interactions existed before particular measurements. And since physical systems have been interacting continuously since the earliest moments of the universe, this suggests that relational facts have always existed, even in the absence of observers. And this view avoids the idea that observation creates reality, while also avoiding the idea that reality consists of a single universal set of properties defined in all contexts, and instead proposes a layered picture where different sets of properties become meaningful in different interaction situations. And this approach also helps explain why quantum descriptions can depend on experimental context without implying that reality is subjective. And it shifts emphasis away from observers and toward physical relationships. And like other interpretations, the relational view does not change the predictions of quantum mechanics, but offers a different conceptual lens for understanding those predictions. And its value lies in showing that the apparent tension between observation and existence may arise from assuming that properties must be absolute. And once that assumption is relaxed, a coherent picture of pre-observation reality becomes easier to maintain. And this prepares us to examine more carefully what physics itself can and cannot legitimately claim about the nature of reality.
At this point, it becomes important to separate three different layers of discussion: what experiments show, what physical theories calculate, and what interpretations say those calculations mean. And confusion often arises when these layers are blended together. And experiments provide concrete outcomes, such as detector clicks, interference patterns, and statistical distributions. And these outcomes are objective in the sense that they can be recorded, repeated, and compared by different observers. And physical theories provide mathematical frameworks that successfully predict these outcomes, often with extraordinary precision. And interpretations attempt to connect the mathematics to a conceptual picture of reality. And while interpretations are constrained by experimental results, they are not uniquely determined by them. And this is why multiple interpretations can coexist while making identical predictions. And recognizing this structure helps clarify the original question, because physics itself does not directly assert that reality only exists when observed. And what physics asserts is that certain properties cannot be predicted with certainty before specific interactions occur. And this is a statement about limits on prediction, not necessarily about limits on existence. And when people say that quantum mechanics shows reality is created by observation, they are usually adopting a particular interpretive stance, not stating an experimentally established fact. And this distinction matters because it prevents the conversation from drifting into exaggerated claims that go beyond what the science supports.
And a more careful reading of quantum theory suggests a quieter conclusion, that the universe operates according to probabilistic rules at small scales, and that interactions play a central role in shaping which properties become definite. And this does not require that nothing exists prior to observation. Instead, allows for a continuous underlying physical world whose detailed features become accessible only through interaction. And keeping this layered perspective in mind provides a stable foundation for approaching the remaining questions about what can reasonably be said regarding pre-observation reality.
A useful way to think about the question of whether reality existed before observation is to shift attention from individual properties to physical processes, because processes occur continuously regardless of whether they are recorded, and stars burn, particles collide, and fields fluctuate throughout the universe without waiting for measurement. And these processes involve energy exchange, momentum transfer, and causal influence, and all of these are features of physical reality. And if such processes were not occurring, there would be nothing for measurements to detect in the first place, and this simple observation supports the idea that the universe does not depend on observers in order to exist. And at the same time, quantum mechanics tells us that the detailed outcomes of some processes cannot be predicted with certainty, and that only probability distributions can be calculated. And this combination leads to a balanced view, where reality exists continuously, but some aspects of reality are only defined probabilistically until interactions take place. And this is different from saying that reality is created by observation, and instead suggests that observation reveals particular aspects of an already ongoing physical world. And another way to express this is that observation selects from among possible manifestations of underlying processes rather than generating those processes from nothing. And this perspective aligns with how science treats other probabilistic phenomena, such as thermal motion or radioactive decay, where unpredictability does not imply non-existence. And recognizing this distinction allows us to approach the original question with less drama and more precision. And it encourages a view in which the universe is fundamentally real, while our descriptions of that reality are limited and context-dependent. And this prepares us to consider what physics can confidently claim and where it must remain silent. When physicists speak carefully about the foundations of their field, they often emphasize that physical theories are models rather than literal photographs of reality. And a model is a structured mathematical framework designed to organize observations and produce reliable predictions. And its value is measured by accuracy and consistency, not by how closely it resembles everyday intuition. And quantum mechanics is one of the most successful models ever developed. And yet it is expressed in abstract mathematical language that does not easily map onto ordinary concepts such as objects, locations, and trajectories. And this mismatch between mathematics and intuition is a major source of confusion when people try to interpret what the theory says about existence and observation. And one common mistake is to treat the symbols of the theory as if they directly describe physical objects, when in fact they represent elements of a calculation system. And for example, the wavefunction is a mathematical object that allows physicists to compute probabilities for different outcomes.
and whether this wave function represents a physical wave, an informational structure, or something else entirely is not specified by the theory itself. And this means that statements about what the wave function truly is belong to interpretation rather than experiment. And recognizing this distinction helps prevent exaggerated claims about what quantum mechanics proves regarding the nature of reality. And it also highlights a deeper point, that physics as a discipline is primarily concerned with predicting relationships between observations, not with providing final metaphysical descriptions of what exists. And this does not mean that physics avoids questions about reality, but that it approaches them indirectly through operational definitions and testable consequences. And with respect to the question of whether reality existed before observation, physics can confidently state that physical processes occurred long before observers appeared, because evidence from cosmology shows stars forming, galaxies evolving, and radiation traveling through space billions of years before life emerged. And these processes obeyed the same physical laws that operate today. And at the same time, physics acknowledges that certain microscopic properties cannot be assigned definite values within the theory prior to interaction. And this reflects a limitation of description rather than a declaration that nothing exists. And bringing these points together leads to a calm and careful position, that reality did not suddenly appear when observed, but that our ability to assign specific properties to systems depends on interaction and measurement. And this balanced understanding allows us to respect both the success of quantum mechanics and the intuitive sense that the universe existed long before anyone was there to look at it.
Another helpful way to approach the question of pre-observation reality is to consider how physics treats unmeasured systems in practice. Because in everyday research, physicists routinely make predictions about systems that have not yet been observed, and these predictions are based on applying physical laws to known initial conditions, and then calculating how the system should evolve over time. And this practice would make little sense if scientists believed that systems had no reality prior to measurement. And instead, it reflects an assumption that physical systems exist and evolve even when no one is watching. And quantum mechanics does not overturn this working assumption, but modifies how predictions are expressed. And instead of predicting single outcomes with certainty, it predicts probability distributions for possible outcomes. And these distributions evolve smoothly according to mathematical rules. And this smooth evolution occurs regardless of whether a measurement takes place. And this means that quantum theory describes continuous physical processes, not gaps where nothing exists. And another important point is that many quantum experiments rely on preparation procedures, where a system is placed into a known initial state, allowed to evolve for some time without observation, and then measured. And the results depend strongly on the details of that unobserved evolution. And this would not be possible if the system had no physical state during the unobserved interval, and instead suggests that the system possesses a well-defined quantum description even when it is not being measured. And this description may involve superpositions and probabilities, but it is still a structured state governed by physical law. And this supports the idea that reality existed prior to observation, even if it was not classical in form.
And in this sense, the deeper lesson of quantum mechanics is not that reality depends on observation, but that reality is described by a different kind of structure than classical intuition suggests. And this structure becomes visible through interaction, but does not originate from interaction itself. And holding on to this distinction helps keep the discussion grounded and avoids turning a technical theory into an exaggerated philosophical claim.
Cosmology provides an especially strong perspective on the question of whether reality existed before observation, because it deals with the large-scale history of the universe, including periods when no observers, no planets, and no complex structures existed. And according to a wide range of independent measurements, the universe began in a hot, dense state and has been expanding and cooling for billions of years. And during its earliest stages, simple particles and radiation dominated, long before stars or galaxies formed. And yet, physical processes such as nuclear reactions, particle interactions, and gravitational clustering were already occurring, and these processes left measurable traces that we can observe today, such as the cosmic microwave background radiation and the relative abundances of light elements. And the existence of these traces would be impossible if physical reality required observation in order to exist, because there were no observers present to bring these early conditions into being. And instead, the evidence strongly supports the view that the universe evolved according to physical laws independently of observation. And quantum mechanics is fully consistent with this cosmological picture, because it provides statistical rules for how early universe processes unfolded, and these rules can be used to calculate predictions that match observations with high precision. And this means that quantum theory does not imply that the early universe was unreal or undefined, but rather that it was governed by probabilistic laws. And this distinction is important because it shows that probabilistic description does not equate to non-existence. And from this cosmological perspective, the question of whether reality existed before observation receives a quiet but strong answer, that physical reality existed long before observers, even though our descriptions of that reality must be expressed using probabilistic mathematics at small scales. And this cosmological evidence provides a firm anchor point in a discussion that can otherwise drift into abstraction. Another angle from which to examine this question is to consider how physical laws themselves are discovered and tested, because the entire scientific method is built on the assumption that regular patterns exist in nature, whether or not anyone is actively observing them. And experiments are designed to reveal these patterns, not to generate them. And when scientists perform measurements, they are not creating laws, but uncovering relationships that appear to operate consistently across many different conditions, locations, and times. And this consistency would be difficult to explain if reality only existed at the moment of observation, and instead suggests that physical processes unfold according to stable principles that do not depend on being witnessed. And quantum mechanics fits within this broader scientific structure, even though its descriptions differ from classical intuition. And when quantum predictions are tested, they succeed because the underlying processes behave in regular ways, not because observation brings those processes into existence. And another important point is that quantum experiments can be automated and left running without human presence, and the recorded data still displays the same statistical patterns.
And this shows that outcomes do not require awareness, intention, or attention in order to occur, and they only require physical interaction between systems. And this further weakens the idea that consciousness plays a fundamental role in creating reality, and instead supports a view in which reality is physical, lawful, and continuous, while observation is a method for accessing certain aspects of that reality. And within this view, the strange features of quantum mechanics do not point to a fragile or observer-dependent universe, but to a universe whose underlying structure is more subtle than classical models assumed. And subtlety does not imply non-existence, and it does not imply dependence on minds. It implies that nature operates according to rules that are unfamiliar but still objective. And this perspective allows us to approach the original question in a grounded way, and to say that reality existed before observation, but that reality was not necessarily composed of classical properties in the way we experience today. And this distinction between existence and classical definiteness will remain central as we continue moving forward.
At this stage, it becomes helpful to address directly a common misunderstanding, which is the idea that quantum mechanics places consciousness at the center of physical reality. And while this idea appears frequently in popular discussions, it is not supported by the structure of the theory itself. And nowhere in the mathematical formulation of quantum mechanics does consciousness appear as a variable, a parameter, or a special operator. And the equations describe systems, interactions, and probabilities without reference to minds, awareness, or experience. And the appearance of consciousness in some interpretations arises from attempts to describe subjective experience, not from experimental necessity. And this distinction matters because it separates philosophical speculation from physical theory. And when experiments are analyzed carefully, the factor that determines outcomes is physical interaction, not observation by a conscious agent. And detectors, photographic plates, and electronic sensors all produce the same results, regardless of whether anyone is present to watch them in real time. And this demonstrates that measurement is a physical process, not a mental one. And acknowledging this helps clarify the original question, because if consciousness is not a fundamental ingredient in quantum mechanics, then reality cannot depend on being consciously observed. And instead, reality must be grounded in physical processes that occur independently of awareness. And this does not mean that consciousness is unimportant, but that it belongs to a different level of description, namely the study of biological systems and cognition, rather than the foundations of physics. And keeping these domains distinct prevents confusion and overextension of concepts, and it allows us to say with confidence that quantum mechanics does not imply that minds create the universe. And this conclusion aligns naturally with the cosmological and experimental evidence discussed earlier, reinforcing the idea that reality existed long before observers and continues to exist independently of them.
A further point that helps stabilize this discussion is to recognize that many concepts in physics describe limits on what can be known, rather than limits on what exists. And this distinction is subtle but extremely important because it separates epistemology, which is the study of knowledge, from ontology, which is the study of being. And quantum mechanics places strong limits on what can be simultaneously known or predicted with certainty. but it does not explicitly state that underlying physical systems cease to exist when they are not being measured. And for example, the uncertainty principle places limits on how precisely certain pairs of properties can be specified at the same time, such as position and momentum. But this does not imply that particles vanish when their position is not precisely known. And instead, it means that the theory does not permit a description in which both quantities are sharply defined simultaneously. And this pattern appears repeatedly in quantum physics, where the theory constrains descriptions and predictions without making claims about non-existence. And keeping this distinction in mind helps prevent the slide from cannot be precisely described to does not exist. And this is especially relevant to the question of pre-observation reality, because much of the apparent mystery arises from confusing limits of description with limits of being. And once this confusion is removed, a calmer picture emerges, where physical systems exist continuously, but our ability to describe certain aspects of them is constrained by the structure of the theory. And this picture aligns with how physics treats many other domains, such as chaotic systems, where precise long-term prediction is impossible, even though the system itself is real and evolving. And in this sense, quantum mechanics can be understood as a theory that tells us how nature behaves, not a theory that tells us that nature depends on our awareness. And this perspective allows us to preserve a realist intuition that something exists independently of observation, while also accepting the distinctive features of quantum description. And holding both of these ideas together leads to a more balanced and less sensational understanding of what quantum mechanics implies about reality.
It is also useful to consider how language itself shapes the way we think about these questions, because many of the words we use, such as object, state, property, and existence, were developed in a classical context, and they carry assumptions that may not apply cleanly at the quantum level. And when these words are used without adjustment, they can create the impression that quantum mechanics is denying reality, when in fact it may be pointing to a different structure of reality. And for example, in classical physics, an object is assumed to have a collection of intrinsic properties that belong to it alone, while in quantum mechanics, the theory is naturally expressed in terms of correlations between systems. And this difference suggests that reality may be less about self-contained objects and more about patterns of relationship. And this does not weaken the notion of reality, but changes its emphasis. And from this perspective, asking whether reality existed before observation may be similar to asking whether relationships existed before certain interactions. And since physical systems have always interacted, the answer is naturally yes. And this relational framing helps dissolve the apparent paradox, because it shows that quantum mechanics does not require a blank void that suddenly becomes real when measured. Instead, describes a continuously interacting universe whose structure becomes visible through specific interactions. And language that emphasizes objects with fixed intrinsic properties may therefore be less appropriate than language that emphasizes processes and relations. And adjusting our language does not change the mathematics of the theory, but it can significantly change how we interpret its implications. And this awareness encourages a more careful and less anthropocentric reading of quantum mechanics, where observation is not a creative act, but one type of interaction among many. And within this reading, reality is not fragile or dependent on being watched, but is robust, dynamic, and continuously evolving, even when unobserved. As we move deeper into this discussion, a consistent pattern becomes visible, and that pattern
is that every serious attempt to interpret quantum mechanics while remaining faithful to experimental results allows for some form of pre-observation reality, even though the nature of that reality may differ from classical expectations. And some interpretations describe reality as a single evolving wave function. Others describe it as many branching histories. Others describe it as a network of relational facts, and others leave the underlying picture deliberately unspecified. But none require the conclusion that nothing exists until a human observes it. And this observation is important because it shows that the popular idea that quantum mechanics proves reality is created by observation is not a conclusion of physics, but a cultural interpretation layered on top of the science. And recognizing this helps return the discussion to a calmer and more accurate footing. And from this footing, we can say that quantum mechanics challenges the idea that all properties are always sharply defined, but it does not challenge the idea that something exists. And this distinction may seem small, but it carries large conceptual weight, and it allows us to maintain continuity between everyday experience and fundamental physics, rather than treating quantum theory as a radical break from all previous notions of existence. And at the same time, it invites humility, because it reminds us that our intuitions, shaped by macroscopic experience, may not be reliable guides to microscopic structure. And therefore, reality may exist in ways that are difficult to visualize, even though it exists nonetheless. And holding on to this perspective prepares us to approach the final sections of the series, where we will step back and ask what can reasonably be said, what cannot be said, and why the question of pre-observation reality continues to persist.
As we approach the later stages of this exploration, it becomes increasingly important to clarify what kinds of statements science is capable of making, because confusion about the scope of scientific claims often fuels unnecessary philosophical extremes, and science is fundamentally a method for building models that predict observations. And when those models succeed repeatedly, we gain confidence that they capture important aspects of how nature behaves. However, this success does not automatically grant access to a complete metaphysical description of what reality is in itself. And this distinction matters when discussing whether reality existed before observation, because physics can tell us how systems behave when measured and how their behavior evolves statistically when unmeasured. But it cannot directly step outside its own formalism to declare what existence means in an ultimate sense. And recognizing this limitation is not an admission of weakness, but an expression of methodological clarity. And within this clarified scope, physics strongly supports the existence of a universe that evolves according to consistent laws, independent of observation. And this support comes from cosmology, from laboratory experiments, and from the internal coherence of theoretical models. And at the same time, physics also shows that our descriptions of certain microscopic properties are necessarily probabilistic and context-dependent. And these two statements are not contradictory, and together they form a balanced picture where reality exists but is not obligated to conform to classical expectations about definiteness. And this balanced picture removes the need for dramatic conclusions about observation creating existence, and replaces them with a quieter understanding that observation is one way of accessing an already existing world.
And this understanding aligns with how science has historically progressed, by refining descriptions rather than overturning the existence of the world itself. And this perspective provides a stable foundation for approaching the final questions of the series with clarity rather than speculation.
At this stage, it is useful to slow down and examine the structure of the question itself, because the way a question is framed often determines the range of answers that seem possible. And when we ask whether reality existed before observation, we are implicitly assuming a sharp division between existence and observation, as if these were two completely separate categories. And yet physics suggests that interaction is a more fundamental concept than observation, and that what we call observation is simply a particular kind of interaction in which information becomes stably recorded. And this shift in emphasis changes the character of the question, because instead of asking whether reality exists when no one is looking, we begin to ask how physical systems behave when they are not interacting in ways that produce stable records. And quantum mechanics provides a clear answer to this second question, which is that systems continue to evolve according to well-defined mathematical laws, described by continuous equations. And this evolution does not pause, does not wait, and does not depend on awareness. And this point cannot be overstated, because it directly contradicts the idea that the universe is somehow idle until observed. And another important aspect is that the universe is filled with interactions at all times, and even in regions that appear empty, quantum fields fluctuate, particles exchange virtual excitations, and energy flows through space. And these processes constitute physical activity, and activity implies existence. And therefore, from physical standpoint, it is difficult to construct a coherent picture in which nothing exists prior to observation. And instead, a more consistent picture is that reality is always present, but not always describable in classical terms. And within this picture, observation does not create reality, but selects certain features of reality and renders them stable and communicable. And this distinction allows us to preserve the intuitive idea that the universe existed long before observers, while also respecting the formal structure of quantum mechanics. And this reconciliation is one of the quiet achievements of modern physics, even though it is often overshadowed by more dramatic interpretations.
Another helpful perspective is to carefully examine the difference between existence and description, because these two ideas are often unconsciously merged, and when they are merged, confusion almost always follows. And existence refers to whether something is there at all, while description refers to how we represent that thing using concepts, symbols, or mathematical structures. And quantum mechanics primarily constrains description rather than existence, and it tells us which kinds of descriptions are permitted, which combinations of properties can be assigned together, and which forms of prediction are possible. And it does not state that physical systems stop existing when certain descriptions are unavailable. And this pattern appears repeatedly across physics. And for example, classical thermodynamics tells us that we cannot track the exact motion of every individual molecule in a gas. But this does not mean that the molecules vanish when we lack a detailed description. And similarly,
Chaos theory tells us that long-term prediction can be impossible even in deterministic systems. But this does not imply that the system itself ceases to exist. And these examples illustrate a general principle, that limits on knowledge do not imply limits on being. And applying this principle to quantum mechanics helps dissolve much of the apparent mystery surrounding observation, because it shows that the theory is primarily a framework for organizing expectations about measurements, not a declaration that measurements bring reality into existence. And another way to express this is that quantum mechanics provides rules for how we update our descriptions when new information becomes available. And updating a description is not the same as creating the thing being described. And from this perspective, the question of whether reality existed before observation becomes less paradoxical, because existence is not placed under the control of measurement. Instead, measurement is placed within an already existing physical framework, and this framework evolves continuously according to physical law, regardless of whether it is being monitored. And this view is consistent with every successful application of quantum mechanics, from atomic physics to chemistry to solid-state materials to cosmology. And none of these domains require the assumption that reality switches on when observed. And recognizing this broad consistency strengthens the case for a pre-observation reality, even if the detailed structure of that reality does not resemble classical expectations. And this careful distinction between what exists and how we describe what exists will remain central as we approach the final parts of the series.
As we move toward the later parts of this exploration, it becomes increasingly valuable to slow down and ask what kind of answer would actually satisfy the original question. Because the question of whether reality existed before observation can be interpreted in several different ways, and not all of those ways fall within the domain of physics. And if the question means, did physical processes occur before observers existed, then the answer provided by cosmology, astrophysics, and geology is clearly yes, because we have extensive independent evidence of events that took place billions of years before life arose, such as the formation of galaxies, the birth and death of stars, and the production of chemical elements. And these events left traces that we can still measure today. And if the question means, did physical systems evolve according to lawful patterns before any measurements were performed, then the structure of quantum mechanics also supports yes, because the theory describes continuous time evolution of quantum states even in the absence of measurement. And this evolution is governed by precise mathematical equations, and these equations do not contain any terms that switch on only when an observer is present. And if the question means, did microscopic properties have classical-style definite values before interaction, then quantum mechanics answers no in many cases, because the theory does not assign sharp values to certain properties prior to measurement. And this third version of the question is the one that generates most of the philosophical tension. And recognizing these distinct meanings is important, because without this separation, the discussion can become confused and circular. And once the meanings are separated, a calmer picture emerges, where the universe clearly existed and evolved long before observers, while at the same time, the microscopic structure of that universe does not necessarily conform to classical intuitions about definiteness.
And this combined position does not require choosing a specific interpretation of quantum mechanics, and it does not require attributing any special creative role to consciousness, and instead rests on the empirical success of physical theory and the internal consistency of its mathematical structure. And holding this balanced position allows us to approach the final parts of the series with patience, clarity, and a realistic sense of what science can and cannot claim.
At this point in the discussion, it becomes necessary to slow down and carefully examine what physics can legitimately claim about reality, and to clearly separate those claims from broader philosophical speculation. Because much confusion arises when these two domains are blended together, and physics operates within a specific methodological framework. And that framework is centered on constructing mathematical models that organize observations and produce reliable, testable predictions. And when those predictions are confirmed repeatedly across many different experiments, confidence in the model grows. And however, even extremely successful models do not automatically become complete metaphysical descriptions of what reality is in itself. And this limitation is not a weakness of physics, but a consequence of its design. And physics aims to describe how phenomena behave, not to provide ultimate definitions of existence. And within this methodological structure, physics strongly supports the existence of a universe that evolves according to consistent laws independent of observation. And this support comes from laboratory experiments, astronomical measurements, geological records, and cosmological observations, all of which point to physical processes unfolding long before any observers existed. And stars formed, elements were created, and galaxies assembled in the absence of minds to witness them. And yet these processes left stable traces that we can still detect today. And this alone provides powerful evidence that reality does not depend on being observed in order to exist. And at the same time, quantum mechanics introduces an important refinement to this picture, because it shows that at very small scales, physical properties are not always describable in the classical way. And instead of assigning sharp values to every quantity at all times, the theory assigns probability distributions, and these probabilities evolve smoothly according to precise equations. And this means that while physical systems exist continuously, the form in which they can be described is more subtle than classical intuition suggests. And this subtlety does not undermine existence, but it does challenge classical expectations about definiteness. And another important point is that physics distinguishes between the behavior of systems and our knowledge of that behavior. And quantum mechanics primarily constrains what can be known or predicted, not what can be. And this distinction is crucial, because limits on knowledge are often mistaken for limits on existence. And once this confusion is removed, a calmer interpretation becomes possible. And in this interpretation, reality exists independently of observation, but not all aspects of reality are simultaneously accessible or classically well-defined. And this view avoids the extreme claim that observation creates reality, and also avoids the equally extreme claim that quantum mechanics simply reproduces classical realism at a deeper level, and instead occupies a middle ground where existence is stable, but description is context-dependent. And this middle ground may feel less dramatic than popular portrayals, but it is more consistent with the actual structure of physical theory. And recognizing this helps place the question of pre-observation reality in a more accurate and grounded context, and prepares us to consider what physics does not claim, as well as what it does claim in the final parts of the series.
Now that we have clarified what physics can reasonably claim about reality, it is equally important to clarify what physics does not claim, because misunderstanding often arises from attributing stronger statements to the theory than it actually makes. And quantum mechanics does not claim that reality is an illusion, and it does not claim that nothing exists until measured, and it does not claim that consciousness plays a fundamental role in creating the physical world. And these ideas sometimes appear in popular discussions, but they are not required by the mathematics or by experimental results. And what quantum mechanics actually claims is more restrained. And it claims that certain physical quantities cannot be predicted with certainty prior to specific interactions, and that probabilities must be used instead. And this is a statement about predictive structure, not a declaration about non-existence. Another point is that quantum mechanics does not specify a unique interpretation of its mathematical formalism. And this means that different conceptual pictures can coexist while producing identical predictions. And because experiments cannot distinguish between these pictures, physics as a discipline does not endorse one as the definitive description of reality. And this neutrality is sometimes uncomfortable, but it reflects intellectual honesty. And it reminds us that successful prediction does not automatically entail complete understanding. Within this honest framework, physics remains silent on certain metaphysical questions, such as what existence ultimately is, or whether reality has a single underlying substance, or whether multiple levels of reality coexist. And this silence should not be mistaken for evidence of non-existence or observer dependence. Instead, it indicates that these questions lie beyond the current reach of testable science. And recognizing these limits helps prevent overinterpretation. And it allows us to approach the question of pre-observation reality with appropriate modesty. And within this modesty, we can still say something meaningful. And that something meaningful is that physics consistently describes a universe that behaves as if it exists independently of observation, even though the fine-grained structure of that universe does not match classical intuition. This careful balance between confidence and restraint characterizes the most reliable conclusions we can draw at present.
At this stage, we can begin to gather the threads of the discussion into a quiet, coherent picture, without turning that picture into a final or absolute conclusion. And the picture that emerges is one in which physical reality exists continuously, evolves according to consistent laws, and does not depend on being observed in order to exist. And at the same time, the picture also acknowledges that the detailed structure of reality at small scales is not required to conform to classical expectations about definite properties, and instead follows probabilistic and relational rules. And these two statements are not in conflict, but describe different aspects of the same underlying world. And one concerns existence, while the other concerns description. And throughout this series, we have seen that quantum mechanics does not place observers at the center of the universe, but places interactions at the center. And observation is simply a special case of interaction in which information becomes stably recorded. And this framing removes much of the apparent mystery surrounding measurement and replaces it with a quieter understanding of physical correlation. And from this perspective, the universe does not wait to be seen in order to be real, and it does not switch on when looked at, and instead continues unfolding according to its own internal dynamics.
And this unfolding was happening long before life appeared, and will continue long after current observers are gone. And yet, quantum mechanics also teaches us humility, because it shows that not all questions about microscopic structure have classical-style answers, and some features of reality may only be expressible in probabilistic or relational terms. And accepting this limitation does not weaken the concept of reality, but refines it. And it encourages a view of reality as stable but subtle, lawful but unfamiliar. And this refined realism is perhaps less dramatic than popular interpretations, but it is more consistent with the actual practice of physics. And holding this view allows us to approach the final reflections of the series with calm clarity rather than sensationalism.
Even after forming a coherent and balanced picture, it is natural to ask why the question of pre-observation reality continues to persist so strongly in scientific and philosophical discussions. And one important reason is that quantum mechanics introduces limits that do not appear in classical physics, and humans are naturally unsettled by limits, especially limits on prediction and knowledge. And when a theory tells us that certain outcomes cannot be known in advance, it is easy to interpret this as a statement about existence itself, even when the theory is only making a statement about description. And this psychological tendency contributes to the feeling that something deeply strange is happening, even when the underlying structure is more restrained. And another reason the question persists is that everyday language evolved to describe macroscopic objects that behave classically. And this language carries built-in assumptions about definite properties, continuous trajectories, and independent objects. And when these assumptions are carried into the quantum domain, they often fail. And the resulting mismatch creates the impression that reality itself has become unstable, when in fact it is our classical vocabulary that has reached its limits. And a third reason is that quantum mechanics genuinely reveals that some classical intuitions about properties do not apply at small scales. And this revelation invites deep reflection about what it means for something to exist. And none of these factors require the conclusion that reality depends on observation, but they do explain why the question remains emotionally and intellectually powerful. And recognizing this helps reframe the situation, because it shows that the persistence of the question is not evidence of a broken or paradoxical universe, but evidence of a transition between conceptual frameworks. And such transitions have occurred many times in the history of science, and each time they required patience, refinement of language, and development of new mathematical tools. And over time, what initially appeared mysterious often became understood as a natural consequence of deeper structure. And this historical pattern suggests a cautious optimism, not that final answers are close, but that confusion does not imply impossibility. And until more complete theories are developed, the most stable position remains to acknowledge both the strength and the limits of current physics, and to resist the urge to convert uncertainty into dramatic metaphysical claims. And this calm stance preserves intellectual honesty and keeps the discussion aligned with what the science actually supports.
As we approach the final sections of this series, it becomes helpful to step back and look at the overall shape of what has been explored,
because doing so reveals a consistent theme. And that theme is that modern physics neither denies reality nor reduces it to human perception, but instead presents a picture of a universe that exists, evolves, and follows lawful patterns independently of observation, while also showing that the fine-grained structure of that universe does not always conform to classical expectations. And this dual message can feel uncomfortable because it resists simple slogans, and yet it reflects the actual content of the theory more faithfully than more extreme interpretations. And throughout this exploration, we have seen that quantum mechanics is a probabilistic theory, but not a nihilistic one, and that it constrains what can be predicted, not what can exist. And we have seen that interactions play a central role in shaping which properties become well-defined, but that interaction is a ubiquitous physical process, not a privilege of conscious observers. And we have seen that multiple interpretations of quantum mechanics are possible, but that none of them require the conclusion that reality only exists when observed. And these points together form a coherent landscape in which reality is stable, lawful, and continuous, even if its deepest structure is unfamiliar. And this landscape allows us to answer the original question in a careful and qualified way. And that answer is that physical reality existed before observation, but not necessarily in a classical form. And this qualification matters because it respects both the evidence for an observer-independent universe and the distinctive features of quantum description. And holding both of these elements together avoids distortion in either direction, and it provides a calm resolution that fits the spirit of scientific inquiry, which values precision over drama and clarity over spectacle. And with this perspective in place, we can move toward the final reflections of the series.
In the quiet space created by this understanding, it becomes possible to see the original question in a slightly different light, not as a demand for a single definitive verdict, but as an invitation to examine how human concepts adjust when confronted with deeper layers of nature. And questions about reality and observation have appeared many times in the history of science, often during periods when new theories forced revisions of long-held intuitions. And in each of these periods, the most durable progress did not come from dramatic proclamations, but from gradual refinement of language, careful expansion of mathematical frameworks, and patient reconsideration of assumptions. And quantum mechanics appears to represent another stage in this long process, rather than a final rupture with all previous ideas. And from this perspective, the persistence of the question about pre-observation reality is not evidence that reality is fragile or observer-dependent, but evidence that our conceptual tools are still being reshaped. And this reshaping process does not point toward a universe created by minds, but toward a universe whose underlying structure is more subtle than classical categories allow. And this distinction matters because it changes the emotional tone of the discussion and replaces existential unease with a quieter form of curiosity. And within this calmer frame, we can acknowledge that some aspects of reality may never be fully visualizable or intuitively graspable, and that this limitation does not weaken their existence and does not require us to abandon the idea of an objective world. Instead, encourages a more mature form of realism, one that accepts that existence does not need to mirror everyday experience in order to be genuine. And this mature realism allows us to hold together two ideas at once:
that the universe exists independently of observers, and that our descriptions of the universe are shaped by the tools and concepts we possess. And recognizing this duality helps place the original question in a broader intellectual context and prepares us to approach the closing reflections with calm continuity rather than a search for final dramatic answers.
As we move into the final reflections of this series, it becomes appropriate to step back from detailed mechanisms and return to the broader meaning of the question itself. Because the question of whether reality existed before observation is, at its core, a question about the relationship between the universe and human understanding. And modern physics suggests that this relationship is indirect rather than central, and that the universe is not organized around human perception, but around physical processes that operate according to consistent laws. And these processes were unfolding long before life emerged, and they will continue long after present observers are gone. And this simple fact carries quiet weight, because it places human observation within the universe rather than above it. And at the same time, physics also shows that the universe is not required to conform to the categories shaped by everyday experience, and that deeper layers of reality may behave in ways that resist classical description. And this combination can feel unsettling, but it also reflects a coherent and restrained picture. And in this picture, reality exists but is not obligated to be simple, and observation reveals but does not generate, and existence is primary while description is secondary. And holding these relationships in mind allows us to approach the original question without forcing it into a binary choice, and instead to accept a nuanced answer. That physical reality existed before observation, but not necessarily as a collection of classical objects with definite properties. And this nuance is not a weakness, but an expression of intellectual honesty. And it aligns with how science has advanced historically, through gradual refinement rather than sudden metaphysical reversals. And with this understanding, we are prepared to close the series with a calm statement of where the question stands today. In the end, the question of whether reality existed before observation does not resolve into a simple yes or no, but into a layered understanding shaped by both empirical evidence and conceptual restraint. And physics provides strong and consistent support for the existence of a universe that evolves according to lawful processes independent of observation. And this support comes from cosmology, from laboratory experiments, and from the internal coherence of theoretical frameworks. And at the same time, physics also reveals that the deepest structure of this universe is not required to match classical intuitions about definite properties at all times, and instead follows probabilistic and relational patterns. And these two facts coexist without contradiction, and together they suggest a quiet conclusion that reality existed before observation, but not necessarily in the form that everyday experience leads us to expect. And this conclusion avoids dramatic claims about minds creating the universe, and avoids equally dramatic claims that quantum mechanics secretly restores classical determinism, and instead occupies a middle ground that is stable, modest, and faithful to the science.
And this middle ground does not offer final metaphysical certainty, but it does offer conceptual clarity. And it reminds us that science progresses not by answering every possible question, but by steadily refining the kinds of questions it can meaningfully ask. And in this sense, the persistence of the question is not a failure, but a reflection of the depth of the subject. And the most responsible position is to acknowledge both what is known and what remains open, and to hold that space with patience. And with this perspective, we can allow the question to remain part of an ongoing exploration rather than a problem demanding closure. And in doing so, we remain aligned with the quiet, careful spirit that has guided scientific understanding across generations.
As we come to the end of this session, there's nothing you need to take with you. No ideas to hold on to, no thoughts to finish. The words can fade, just like the day slowly does. If you found this space calming, you can leave a like or subscribe to the channel. It quietly supports more moments like this. For now, let everything settle. You don't need to listen closely anymore. The sound can stay even as attention drifts away. Rest easy and let time continue gently on its own.